Okay. Thank you for tuning in. We are going to go over the next section of the textbook, which goes over a bunch of stuff, but most of it is about how electrons can well, it's just, I guess, more details about electrons in preparation for learning more about chemical bonds. So there's a bunch of little sort of facts and loose ends we need to tie up, and that's the lectures. This talk is going to cover a bunch of different details. Hopefully, you don't get lost. I can't remember what page in the textbook it starts on. I don't have the textbook with me, and so we're just going to go through it and see how it goes. So there's, I think, 5 different things that the textbook covers at this part, and 5 different things that you need to know logically before we move on to ionic and covalent bonds when I get back. The first, which is rules about charges, which you already know from science. I think it's 9, and probably from just being alive, you know these rules, but we'll go over them anyway. More rules about electron shells, and what it means to be an open and a closed shell, which is pretty straightforward as well. We need to sort of take a look at valence electrons again, what that means. Won't take long. Then we need to bring in a different word. And I know it says valence, and then we've been using valence electrons, but the word valence means something different. So a lot of students get confused between when I say the word valence and when the term valence electrons are used. That means something different, so that's kind of tricky there. And then the last thing is ionization energy. So these sort of 5 things are what we are going to be looking at today. Okay, so first off, the rules about charges. What are the rules of static electricity? You already know this, and from this picture down here at the bottom, you can surmise that you see these 2 balls hanging from wires, and they're being forced apart here, and they're being forced apart here, and they're being brought together here. So you can see that you already know the rules. You probably could have guessed what would happen at this part, but the rules are this, that opposite charges attract and that like charges repel. And you can see that down there below. But something that's more often forgotten, even though it is taught to you in Science 10, is that the closer that those 2 charges get, the stronger the force is in between them. So if you were to take these red ones down at the bottom and bring them closer, the force that repels them would get even bigger. Same with these 2. Again, you bring them closer, the force that repels them would be even bigger. Whereas here, they're as close as they can get, but they'd be attracted if they were apart. But the closer they get together, the stronger the force of attraction between them. So the force of attraction is a function of distance, you could say. Okay, and then the last thing is that also if you change the size of the charge, the more force that's pulled in. Now this one is going to be useful because we're going to be talking about the number of protons, and so when you look at the number of protons, then if you increase the number of protons, you're going to increase the size of the charge. I shouldn't use the word size, I should have used magnitude, but oh well. Then the more force it's going to exert. So we already know that a proton amount of like 5 has a certain force. If we increase the proton amount to 10, it's going to have double the force. So those things are important. The closer they are, and the greater the charge gets, the more force that they have. Okay? So bringing in those rules about charges, we need to relook at electron shells. Now, when I say an electron shell, what I'm really talking about is a period on the periodic table. So even though their energy levels don't necessarily line up, sorry for my bad drawing here, okay, but on that periodic table, row 1 is shell 1, row 2 is shell 2, row 3 is shell 3. So these rows will also be called shells, okay, and they're called electron shells, not subshells, but shells. So then there are 7 shells in total, and in each shell, each electron is the same average distance from the nucleus. Okay, so if you look at shells going or electrons going across, you need to pretend that all those electrons going across this row, bad drawing, going across this row are in the same. They are the same distance as the others. I know that they're in different orbitals, like one's in an s orbital, one's in a p orbital, and they're all different. But you need to pretend that in the same row they're all the same distance from the nucleus. Okay. As from the other electrons in that row anyway. So all the electrons in the row above are all considered closer. So think about it like a theater, okay? And Obviously, anybody who's in row A is closer to the stage than the people in row B. So, but everybody in a row, even though they're all in different parts of that row, are the same distance from the front, or from the nucleus in this case. Okay? And then what I want to ask now that you know that, and you know the charge rules from before, is what happens as the number of protons increases. You may want to pause it right here and actually think about this. But what happens to this, I'm going to make it more specific, what happens to the size of the atom? Okay? To the size of the atom as the number of protons increases going across a row. So this is still in one row. Okay, so what could you say about the size of an atom here compared to the size of an atom here in one row? Think about that. Because as it turns out, the answer to that question is that the atom gets smaller. So you take a look at, these are all again from one row, but cutting out the transition metals because they're complicated. And the atom gets smaller. Now, taking hydrogen and helium out of it because they're too small to even look at, you look at lithium, which has 3 electrons in it, okay, and it might surprise you that beryllium right beside it has 4 electrons and it's smaller, and this has 5 electrons and it's smaller, and this has 6 and it's smaller, and this is 7 and it's smaller. So you can see that they're all sitting in the same row, but if you what's happening here is the size of the nucleus inside is shrinking the shell down. So lithium, I mean, you think about that one electron being in this shell out here, it doesn't have very strong pulling power to the nucleus because the nucleus only has 3 protons. So as you increase the number of protons, you're going to increase how tightly compact that atom is. So the size of the atom actually gets smaller. And remember that with atoms, size definitely matters, and so we're going to talk about how size can help us predict a lot of things in chemistry, the size of the atom. So you notice that even though the atomic size number increases, the size of the atom decreases, which is kind of weird. It's counterintuitive. You wouldn't think that it's true, but it is. And it's true all across the periodic table. Notice that the size also, the size also gets bigger as you go down. Okay, so that's no surprise because the atomic number is also increasing downwards. And also remember that this is energy level 1. This is energy level 1. This is 2. This is 3. This is 4. This is 5. And this is 6. Right? So as you increase energy levels, yeah, the atom gets bigger and fatter. But as you go across this way, something different happens. It actually gets smaller. What you're seeing here is a bunch of atoms packed into the same row, but because, sorry, a bunch of electrons packed into the same row, but because the power of attraction to the center is greater, those electrons actually squeeze in tighter. So yeah, so that happens. So neon is this tiny little atom, and lithium, even though it has way less electrons, is this huge atom. And I like to think about the nucleus as power to hold on to electrons. So think about lithium and its power to hold on to electrons. Does it like its electrons? Does it want to keep them? Well, no, it's a metal. So we just talked last day about how metals want to give up more freely. They're willing to give up that electron. Look at lithium. Does it look like it's hanging on tightly to those electrons? No way. Look at fluorine, though. Okay, does it look like it's hanging on tightly to those electrons? Heck yes. Okay, what about neon? Is it hanging on tightly? Very tightly. Remember, it's got a complete set of electrons, so it's extremely happy, and it holds on to those electrons very tightly. Look at cesium. You think that that fat atom is going to hang on to an electron way out there? No, it's going to let go of an electron very easily. Okay, so this again is the most metallic on this chart, and it's the fattest, and this fluorine is the least metallic, and if we ignore the noble gases, then it's also the smallest atom. Okay, so metals are fat atoms too. Anyway, so that's electron shells. Now we'll talk just briefly about open and closed shells. That's really easy. An open shell means the valence isn't full. So if we go back here, all of these have open shells because the valence is not full, whereas all of these have closed shells because the valence is full.